Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. In this one, we're focusing on decision trees. Previously, we looked at correlations. Now we're looking at decision trees, which is a module within SPSS. My name's Charles Quinn. I'm joined online today by my colleague, Rachel. Rachel, just making sure everybody's logged in correctly and fielding questions as we're going along. If you haven't joined any of these sessions before, then as I always say, just be aware that the session is recorded, so you'll be able to listen to it again afterwards. There's a bit of slideware, it's mostly demonstration, but we'll email out a link to you to download the slides after the session's ended. And if you want to arrange a rerun for colleagues, best thing to do is just ask us. Assuming you can get enough of them together, we may be able to do it on a private basis, and you can just send us an email. With regard to asking questions, all the lines are muted, so we can't hear you, but we ask you to use the chat panel. And if we run out of time, we'll follow up with you. We try to remember to check them. Just depends on how many check the chat panels are going along. Just depends on how we're doing for time. But we are used to people, sending us emails and stuff afterwards, or contacting us afterwards, and we can answer their questions fairly thoroughly, I think. If you don't know who we are a gold accredited partner to IBM. We're also a partner to Predictive Solutions and to DataRobot, and we at Smart Vision specialize in statistics, machine learning, data science. Though we work with open source technologies as well. And we are a team of individuals who have very deep experience in the analytical and technology industry, stretching back 30 years. I've worked for SPSS in the past and SAS and IBM as a consultant. That means that we've all got pretty deep experience of applying statistics and decision trees and things like that, machine learning, data science to many different sectors, many different applications within those sectors stretching back over the decades. Now, in this type of analysis, this type of field that we're focusing on here, we're very much looking at using decision trees as a route into the world of classification of propensity modeling and that type of analysis. Within the world of predictive analytics or data science, it's usually most people would encounter decision trees as a method or as a field, as an approach within that context where they're trying to, predict or profile who's most likely to respond or upgrade or defect from a subscription based on some sort of historical data that we have about them. That being said, people do use it for, other types of applications. People use it to try to model things like satisfaction or to, as we'll see, to interpret things like cluster analysis, where you're trying to segment people and trying to create different segments. And decision trees is actually not a bad way to try and figure out what is it that makes one segment different from another. So in many ways, I would say that it's a kind of a modeling about tiers approach, unlike other, say, predictive modeling approaches like logistic regression or let's say gradient boosting or even deep networks and neural networks. It's pretty intuitive and it's very visual. So people it tends to be quite popular people, and it's often used as a sort of gateway when talking about predictive modeling as a way to explain to people how predictive models work, because it's quite easy to get your head around. So, but within the world of data science, predictive analytics, that type of stuff, it tends to be associated with classification modeling, prediction, propensity, as opposed to things like cluster analysis or association analysis or sequence analysis or forecasting like time series analysis. So decision trees are used extensively and widely within data science and predictive analytics. And as I say, they can be used to build profiles of people because they're kind of a profiling tool. That they give you these very nice visual representations, very like family trees, where you can say this is the profile of this group. They can find key behavioral segments within those because each element, each node in the tree refers to a group, a subgroup within the data. So it's kind of key behavioral segments. It's also finding actually key factors, really, because decision trees are very good at ignoring variables or factors which really don't help. And as a result of that, they can, in theory, be used as predictive models. They can be used as predictive models um, because you can pick up a decision tree, apply it to a new data set based on the same types of factors, and get it to generate scores where you get it to generate likelihood values or probability values or propensity values. And it can also be expressed simply as a series of rules. So you can show them visually, but you could turn that visual representation into a series of rules if you're in this group and you're in that group and your score for this variable is higher than a certain threshold and you're also in a subgroup of that, then you have an X% chance of this occurring or something like that. So that means as rules, they can be converted into languages like SQL, which is used in database scoring, and SPSS syntax and R and lots of other different types of languages. So they're very popular because they're a fairly visual representation of modeling, of multivariate models, and they're relatively easy to understand compared to other types of modeling techniques. So a good way to start this introduction to decision trees is to look at a really simple and very famous example. There's a data set out there. You can download it off the internet. If you look for the Titanic data set, you'll find that there's data sets out there in various guises refer to the RMS Titanic and refer to survival on the Titanic, people who survived and people who did not survive. And you might well ask yourself, what are the most important factors determining survival based on that data set? And if you do that, you'll find that, people 32% survived, 68% did not survive that incident, the sinking of the Titanic. And most people, if you ask them in a room full of, full of people, what do you think are the factors which drove survival on the Titanic? They pretty much can guess it straight off. They can say, well, I would imagine it's going to be something like whether or not you're male or female. I'd imagine whether or not you're like an adult or a child. And I'd imagine it might be something like what class you were traveling in. Okay. And they'd be absolutely right. These are the three primary drivers in the data set that help you explain, or help you predict who survives in the Titanic and who didn't. Um, when it becomes more difficult is when you ask people, what do you think is the most important factor? You know, is it gender, is it age, is it class? And they tend to disagree at that point. They're kind of guessing a bit. Now here we have effectively a little table here. Did survive, did not survive. If we split that table by one of these factors, what we're doing is we're creating a crosstab. So this is here's the gender variable, the sex variable here, males and females. We've got a little crosstab, and we can see that 26% of, let's say 27% of females did not survive, compared to 78.8% of males, nearly 79% of the men did not survive. So quite a big difference there. Bear in mind, of course, that there were a lot fewer females than males. There were only 470 women compared to 1,700 men. That's something that the movies tend not to reflect very well. They tend to have a much more even split, but it was a minority of females. And if we wanted to figure out whether or not this factor is, to use the dreadful term, statistically significant, we might do something like associated with a crosstab, might do a test associated with a crosstab, which is called the chi-square test. And the chi-square test is something that we talk about a lot. We use it as an introduction to our, if you look up if you want more information about this, you can look up our webinar, which will already be available on YouTube, called How to Interpret Significance Test. One of the first things we look at is chi-square and how that's calculated. But chi-square basically tells you the probability of getting a result as extreme as the one observed, assuming that gender made no difference to your survival. What that means is that it is possible, theoretical, that this difference of 73% survival of women compared to only 21% of men, it is possible that's just a fluke, that's just random. I mean, it's not very likely, as you can guess, with this number of cases, but it is possible. And what the chi-square test does is it allows you to calculate, assuming it is possible, and assuming that in fact gender was unrelated to survival, assuming it's possible, how often you would see a difference as big as that. Okay, and it shows it to you as a probability value labeled sig. And the thing about the probability value is that it's a really small number, so it doesn't show you the full number because it would in fact be 0.000000. It would never be actually zero. It is possible that, but it'd be a really small number, and that would lead you to say that this is probably statistically significant because it's less than the threshold. Most people choose a threshold of 0.05. Now that's based on a chi-square statistic and also based on something called the degrees of freedom. The chi-square statistic basically looks at what you got, this difference is 73%, 21%, and calculates how far away that is from what you would expect to get if men and women, if there was no difference in the survival rates of men and women. Let's say that 35% of women survived and 35% of men. Let's say that was if we were equalizing it, how big a difference is. And the bigger the difference that is, then the bigger the chi-square value. Now, it turns out that what decision trees use is a chi-square test. One of the first decision tree we're going to look at, one of the most famous ones, uses a chi-square test to try and figure out which variables make a difference to, in this case, to this key outcome, which is survival. And it actually uses not the chi-square value, it actually looks at the significance value, the probability value, but I'm just highlighting the chi-square value here because it's easy to see that a large chi-square value is associated with a very small significance value. Let's compare and contrast that to the next factor. We look at age, adult and child. And here the difference is not as big as the difference between male and female, 73%, 21%. For adults, it was 31% survival. And for children, 52% survival. Not as big a difference. Chi-square value is therefore smaller, but still statistically significant, still 0.0000. It's saying, you wouldn't see a difference as extreme as this very often in a world where age made no difference to people's survival. So you might conclude from that age, that the idea that age is unrelated to survival is not credible. And you would regard this as statistically significant. What happens when you have more than a two category outcome here? This is a 2x2 crosstab. Survive, did not survive versus adult versus child. Well, Pearson chi-square has to adjust for that. The degrees of freedom refer to the number of cells in the crosstab. It's actually the number of rows minus 1 multiplied by the number of columns minus 1. Here we have 4 columns and 2 rows, so that's 1 multiplied by 3 degrees of freedom. It adjusts for that. And it says, you can see again some big differences here on survival. Look, 62% of first class travelers survived, 41% of second class travelers survived, those traveling in second class, 25.2% of those traveling in third class survived, and 24% of the crew survived. Okay, so again, this is statistically significant. What the decision tree allows us to do is to kind of put these factors all together and build a profile. And if we were to build a decision tree based on these 3 factors, what we find is that it starts to choose what it thinks is the most important factor hierarchically and say, that's what I'm going to split everything else by. And in this case, it splits it by the variable gender or sex. Okay, it says that's the biggest factor because that's got the smallest p-value. You can't see the p-value here because it's gone 0.000, but basically largest chi-square and degrees of freedom allows us means that that's the most significant. And it starts off with what it calls the dependent or target field. That's the thing that we're trying to explain, which is whether people survive or not, which we can see up here. It always shades the larger group. It just shades. It says the larger group did not survive, 67.7%. The baseline survival rate was 32%. That's 711 people off 2,201 people survived, passengers survived. And then it says, okay, I'm going to split the data. These 2,201 passengers, I'm going to split into 2 groups. And the men are over here and the women over here. And it says, okay, the majority of men did not survive. So I shade that. And we can see it's just exactly the same numbers as we saw earlier in our crosstab. We can see that 21% survived. The larger group for the females is the people who survived, so that's shaded, and that's 73%. It also starts to call these groups nodes, and it gives them a number. So this is node 1, this is node 2, and this is showing the predicted survival outcome for women, 73%. Now at this point, it's basically got two samples of data, and it can continue to split the data independently of one sample. So the men is now split further, and the women are now split further by any other factors that it can find in the data, which help explain the variability. In fact, which are still statistically significant. And when we unfold the whole decision tree, this is what it looks like. This type of decision tree, because it's based on chi-square, is called CHAID, and it stands for chi-square automatic interaction detector, because it's an automatic calculation of chi-square, and it's automatically looking at interactions and it's detecting them. And here we can see on the male group and the male branch of the decision tree, it splits it by age, and it says that's actually statistically significant. It says, look, if you're a male adult, 20% survival. If you're a male child, 45% survival. And it does not split the children any further by that group. There's only 64 in this case. Keep an eye on this. Remember that the size of the box does not reflect the number of cases in it. So there's 1,600 cases in here. There's only 64 in here. You can see this in the total. But it doesn't split the children any further because it can't find any other factors, or the group size has got too small and it's hit a rule where it says, okay, you're not allowed to go smaller than, say, 50. And if I can't split this without creating a group size which is larger than 50. So in the adult males here, it says, okay, there's still some power here. There's still other factors we can use to split this. And it splits the 1,667 adult males into 4 groups. And we have first class survival of adult males, 32%. Second class survival, second class travelers, adult male travelers, 8.3%. 16.2% in third class. And 22.3% of crew, adult male crew survived. Now, what's interesting is it's very good at finding exceptions to the rule, because you remember back here, we noticed that the people who were least likely to survive was in fact third class, people traveling in third class. But there's variability in that. There's women traveling there, there's children traveling there. It turns out the group that was least likely to survive was actually second class adult males. And only 14 of them survived, 8.3%. So it's really good at finding these exceptions to the rule, the general rule. Over in the female branch, notice that it does not split by age. Why is that? Well, presumably because either there weren't enough female children, and that would have violated the rules and said, that it would create a group size which is too small, or that age was not statistically significant. So one of those two rules. And it meant that your survival rate, if you're a female child or a female adult, was no different, whether or not you're an adult or child. So it doesn't use it as a predictor. So again, another exception to the rule. And the other thing it does is it notice very cleverly, it takes the class variable, and if it finds groups within the class variable that are not different from one another in terms of their statistical significance and likelihood to survive, it groups them together. So it's saying that women traveling in first class, 97% survival. Women traveling in second class or crew, 87% survival, because there's no point splitting them. It doesn't make a difference. Their survival rates are too similar. Women traveling in third class, 45.9% survival. So it's really useful if you have like an ordinal field like region or product type. It will find, the groups that kind of coexist, that group together, that aren't different from one another statistically. What we end up with in this tree is we end up with terminal nodes. A terminal node is a point whereby you can't go any further because you've hit a rule or it can't find any more statistically significant groups. And that means that there are actually 1, 2, 3, 4, 5, 6, 7, 8 dead ends, if you like. This is where you can't go. These are terminals. And that means that this model would generate 8 separate probability scores. So that's it. If the probability scores would be 32% survival for here, this group for node 8, 8.3% survival for node 9, 16.2 survival for node 10, 22% survival for node 11. It would be 45% survival chance for node 4, 97% survival chance for node 5, 87.6% survival for node 6, and 45.9% survival for node 7. So it would only generate 8 probability scores, but these 8 scores would effectively, you could then pick this tree up and apply it to a new data set and say, what's the probability of them surviving? Okay. So that's how it's working. Notice that within our data set there, we didn't have any continuous data, we didn't have scale data. I mean, there is data sets out there about the Titanic where you have like the amount of money that they spent on their ticket, which is going to relate, of course, to the class or something like that. Or you could have the number of people traveling in their group or something like that. And again, decision trees very, very cleverly, they will actually split a continuous variable into groups for you. So what it does is it creates deciles. So here we have who buys a financial service. This is our key outcome. We've got 1,599 records in our data set. 56.4% of them bought the financial service. And we can throw in a variable like the amount of money they have in savings or investment and find that that does indeed affect or does help us predict people's likelihood to buy that financial service. But because it's a continuous number and it has many, many individual values, it splits it into deciles so that everybody's in 10% groups, 10% cases each. And then as if it was a 10 category rating scale or something like that, it then simply groups adjacent groups together, which are not statistically different from another one, and thus finds the thresholds within this variable where it makes a difference. So you can imagine how this would be really useful if you were saying, I don't know, a discount value or something like that, and you're trying to figure out at what point do people really start to buy a service based on discount or based on price or something like that. So we're saying here that, for example, if their amount in savings or investment is less than or equal to 4,395, then only 28% of them buy the service. But if it's between 4,395 and 6,150, it's 48% buy the service. If it's 6,150 up to 8,000, it jumps to 63%. And if it's more than 8,000, it's 78.1% buy this savings or investment, buy this financial service. Really good at finding the thresholds for you. So again, allows you to incorporate continuous and categorical data. Okay, with that in mind, having introduced the concept, we can build it as a decision tree ourselves. And I've got a data set here called insurancetrain.sav. And you can see that I have a mix of variables like the age of customers, their income, the number of children, their disposable income, which is just their income divided by the number of children, taking into consideration the number of children that they have. If they have 0 children, their disposable income is equal to like exactly the same as their income. And if they've got 1 child, there's some sort of penalty that's paid for it. They say, okay, disposable income is about 13,000 there. So you lose by 4,000. What their gender is, what region they live in, their marital status, whether or not they've got a car, whether or not they've got a savings account, whether or not they've got a current account, whether or not they've got a mortgage. And then the key thing is, did they buy home insurance for us? And the idea here is that, the people running this analysis are trying to find the profile of the individuals who will buy home insurance, presumably so that they can then target people who have a similar profile using the decision tree to make a prediction about who's going to buy the service. How many cases we got? It's a very small sample size, it's only 300, okay? Let's just look at the home insurance variable itself. Let's right click on it and just see how many people we've got. Okay, it's about 55%, 45%. Again, this is a bit unusual. It's a bit contrived a little bit. Sometimes people use a balanced data set like this. We've got kind of equal numbers of cases in both groups, close to equal numbers, 55, 45. But very often when you're working in marketing, something like that, you might only have like 1% of people in one of these groups, and 99% might be in the other group. And because you only get like a 1% response rate, decision tree will still work on that basis. You just need to be aware that that your baseline is 1%. Some people are going to have Some groups are going to have a less than 1% chance of responding to the offer. Some people are going to have a 3% chance of responding to the offer, which still means there are a 97% chance they won't respond to the offer, but they are three times as likely as the baseline, three times as likely as average. So here we've got almost a 50-50 split. 45% people have responded to the offer in this example. If we want to build a decision tree, and we could do like a crosstab here and say, oh, let's do like a little crosstab, and even before we do the decision tree and say, does region affect home insurance? Okay, let's look at region here. And I'll even ask for this is row, so I'll ask for some row percentages, and I'll ask for statistics. And ask for a chi-square test. This is what a crosstab's doing in the background, and it's saying, well, 48% of those in inner city buy home insurance compared to 49 point those who don't buy. Sorry, 48% of those who do buy home insurance or do buy home insurance are in the city compared to 49% who don't. And the differences are quite small between these groups. It's quite small, so it's not statistically significant. We wouldn't expect this. We certainly wouldn't expect this to be the first variable that goes into our decision tree. It might become more relevant, of course, when you start to split it by males and females and stuff like that. Let's have a look anyway. Let's go to analyze. I'm going to go down to classify and down to tree and call that up. So we're going to do that. So um, let's have a look at tree again. Sorry, I had distracted. Just classify a decision tree. Call up this tree. So our dependent variable here is there's always some key field, of course. It could be response to a campaign. It could be a level of satisfaction. It could be survival on the Titanic. It could be survival from surgery. It could be, people's defection. It could be likelihood to recommend you to a customer or to a friend. It could be failure of a machine part, some sort of key field. I'm going to pick up everything else and just treat it like a cement mixer and chuck everything in. And I'm just going to run with a basic, just the absolute default settings on this tree, and we'll see what happens. Click OK at that point. You can see the growing method here is CHAID. There are, in fact, more than one algorithm here driving decision tree. We'll come back to that later. Click OK at that point. We'll run that, and it gives me a model summary here telling me that the maximum tree depth was 3. It's basically telling me what the rules were around the trees, around the decision tree, the default rules were. We'll come back to that in a moment. It tells me it created 6 nodes, only 4 of which are terminal nodes, and it only went to a depth of 2. So in other words, it created a really simple tree. And there we have this really simple trees created. There we go. We only had 300 cases in this tree. But there's a really simple tree. I'm gonna zoom into it, show you it. So that's what it looks like. And just to show you that what I normally do is just double click on it and open it into its own little tree editor. And we can use this as an example. So the first thing is it's saying the main factor is the number of kids that you've got. So if you've got like 0 kids, that's less than or equal to 0, then 35.9% of people buy home insurance, compared to 45%. So they're less than average likely to buy home insurance. Whereas if they've got 1 kid, because this is 0 to 1, then they're 85% likely to buy home insurance. And if they've got more than 1 kid, then it drops again to 32% likely. So it's actually people with 1 kid are the most likely group to buy it. And it's non-linear. It's not like the more kids you have, the more likely you are to buy it. But of those who do have more than 1 kid, their age is a big factor. So if they're aged over 41, then 54% of them buy home insurance. And if it's less than or equal to 41, it's only 12% buy it. So these are quite stark differences here. And remember, the group sizes started out with 300. There's 128 in that group, 62 in that group, 110 in that group, and then we split it down off that 110. There's only 57 here and only 53 here. Something that I would be remiss of me not to point out is the fact if I go to view, if I go to options here, it's options. I prefer to put on ranges as text. I tend to switch that on because it's sometimes easier to interpret these ranges. It just puts little labels. There's 0 or less. That says higher than 0 through 1, and that says higher than 1. So if you're having difficulty trying to interpret these, how these ranges are shown. Okay, so it's a very simple tree. What else did it produce for us? Well, it produced some other output here. It produced a risk estimate and it produced some prediction. It says using this simple tree, I can be accurate 80% of the time in the no group and 60% of the time in the yes group. Now, I'm not a big fan of this classification table, generally speaking. The only time it really only makes sense is when you've got a 50-50 split in your dependent variable. Because obviously, if you had like a 1% to 99% split, um, it's never going to predict anybody to be in the response group. If you're looking at people who are going to respond to a marketing campaign, it's never going to you're never going to be predicted to be a responder because you're never going to find a group that's got a more than 50% chance of responding. If your baseline likelihood of response is like 0.5%, 1%, even if you find one where people were 10 times as likely to respond on average, so they go to like 10% or 5%, it still means there's a 90% chance they won't respond. So they'd still be predicted to be a non-responder. So this classification table, sometimes called a confusion matrix, I really don't pay a lot of attention to it unless you've got an even split in the data here. And we've got close to an even split. Maybe it works a little bit better. But people get very disappointed when they run decision trees and go, oh, look, it hasn't predicted it very accurately. Well, that's just because in order to be predicted to be in the yes group or in the no group, it has to be more than 50% confident you're going to belong to that group. So what else can we do in this? Well, there's a few extra things we can do here. We can actually ask it to put in charts, so it can show it as a chart where red is no and blue is yes. We can mix the charts and the percentages sometimes, so it looks like a sort of filtration system. You can move these around, so you can have it sideways or the other way around. Sometimes that's easier. And you can click on individual nodes and zoom into them a little bit and change the colors and the text and stuff like that associated with what the yes looks like. And maybe yes should be green and apply that, and no blue and red should be no if you've got a dark red or something like that. You can do that. You can play around that sort of stuff. You can call up these numbers and see these values. If you've got a really big tree, which we haven't here, it's sometimes hard to navigate around it. So you've got this little tree navigator. So it's worth playing around with these values. I tend to use the zooming in commands a lot, so you can see it. Let's rerun the tree. Let's go back to analyze and then to classify and see if we can get a better tree out of it. And we'll go to the tree again. Here it is as before. Why did it stop? Well, it stopped either because none of these other variables were statistically significant or because it hit a rule saying you're not allowed to go into group sizes that are smaller than a certain amount. And that's what's actually happened. That's all controlled under the criteria button here. So I click on criteria. You can see that it says parent node and child node. Well, the parent node is anything above a node that splits, anything above a sub node. That's the parent node to that child node. And if that child node then split further, then that child node would be the parent node to the next child node. So if I go here and I say, look, it's saying you can't create a child node. You can't create a node that has less than 50 cases in it. Which is given that we've only got 300 records in the data. It's quite a small sample size. It's quite restrictive. So I might say, look, I'm gonna give you a bit more freedom and say I'm gonna change that to 20 and 10. If I change that to 20 and 10, click OK, then you get, as you can see instantly, you're giving the tree more freedom. And now you need to zoom into it. You can see it. Now it's saying, okay, I'm still splitting by number of children, but because I've got more freedom to create smaller group sizes, you can see that for those who have 0 kids, 35% chance likelihood of buying the financial product, buying insurance. In fact, if they're not currently married, that jumps to 68%. And if they are currently married, it drops to 19%. If they're not currently married and they are a mortgage customer, then it drops to 20%. But if they're not currently married and they're not a mortgage customer, it jumps to 93%. And the same over here, we've got like a yes group over here, people who are currently married, and it's saying, well, if they're not a mortgage customer, it's 10% chance. If they are a mortgage customer, it's 40% chance. So it's finding all these differences. Here it's choosing under the people who do have one child, it's using their estimated income. It's saying, well, look, if their estimated income is either more than 15,499, then 96% buy it. And in fact, if they're a savings account holder, all 37 of them in that group bought the product. Over here, it's using disposable income. It's saying, okay, if you've got more than one kid and your disposable income's greater than 14,000, then 91% buy this product. So, it's really zooming into it, and you can say, well, just show it to me. It's almost like a filtration system. You can zoom out. It's almost like it's trying to create the purest red and blue groups. It's like you're filtering sand. And in many ways, that's exactly what a decision tree is trying to do. It's like you're trying to filter, create the purest groups that are possible. And in fact, purity is a measure that's used in some decision trees. They call it purity, where they're trying to create the purest groups. Here it's splitting the data because it's basically doing multiple crosstabs at this point. So that's interesting. That's now the accuracy's gone up in this classification table. As I say, I don't really tend to pay a lot of attention to it. But if I go back to this decision tree using the dialog recall box button here, what else can I do? Is there other stuff I can ask for now that we've introduced this? Well, in criteria here, I could say I could go to the Chade model here and I could say, look, in order for it to merge groups together, I can say, look, that's a bit up, this is you're being a bit kind to them, giving them a likelihood, a probability value, what's called an alpha level of 5%. I want to be a bit more strict and say it has to be at least 1% for merging and splitting a node. Would that make a difference? I don't think it will make a difference. I think they're pretty similar. Is it a bit different? Savings account holder. Yeah, that one's changed because yeah, why was that? Because the p-value, let's look at the p-value, let's zoom in here. The p-value down here to split that was 0.019. And I changed the criteria and says, nope, it has to be lower than 0.01. So that one was then taken out. I've made it more strict. So you can play around with that. Say I want everything to be really strict. I could go back to this and go to the criteria again, and I could say, okay, intervals, and I could say, well, look, it splits it into 10 intervals of 10. So age, estimated income, and number of children, and estimated disposable, they're split into deciles. I could go finer and say split it into vintiles, which are 20ths. That might make a difference, might make a difference. You can play around with these factors. Might find more subtle inflection points. So it's kind of about, whether or not you want a kind of general tree or whether or not you want something that's quite specific. Now, why wouldn't I just say, okay, look, let's just go down to like, let it go down to depths of, well, let's go down to 10 and 5. I'll just do that. 10 and 3, 10 and 5. This is a concept in statistics called overfitting. It means that when you allow the tree to go down into small group sizes, which are so small that they could just be, they could just be idiosyncrasies of the sample that you're what they call training the model against. And as a result of that, the larger the group sizes, the more stable the model will be, but not necessarily the more accurate it will be, because a stable model means that when I apply it to a new data set to make predictions, it's more likely to give similar predictions. Whereas an unstable model or an overfitted model, which is one that's based on sizes which are really, really small, like the group sizes of 5 or 3 or something like that, it might produce really stable predictions on your sample data set, but when you actually try to apply it to a new data set, the predictions are no longer as accurate. That's called overfitting. And there are different approaches used in statistics to get around that. There is a thing called a random forest, which, as you can guess, implies that more than one tree is built. And a random forest tries to get around overfitting by never letting the decision tree see all of the data. So wouldn't let it see all 300 records of data. Let's say it only showed it 250 records and it built a tree. And then it did another random sample of 250 records. And it built another tree. It did that again and again and again, so it ends up with 100 trees, effectively a forest. Then it combines all the average scores together. This is an attempt to get around overfitting by building many little smaller trees, if you like, or smaller trees to make a larger forest. And indeed, from that, many different machine learning algorithms like gradient boosting and stuff like that are built. So decision trees are kind of the origin story of those types of algorithms, those types of approaches. But they're still very useful. Very, as you can see, very visual, very useful way to visualize your data. If I go back to my decision tree again, what else can I do? Well, if I go into categories here, notice that I haven't told it which one is my key field. I'm saying, look, I really interested in this field. Yes, people who buy the decision tree, just by checking that and just by telling it that that's my key field and running that again means that the output changes. I get the same tree that I got previously, but now it's giving me a little table of nodes. And the little table of nodes here is saying node number 7 is your best node because look, the response rate is 96%. Where is that? Well, we can double click on it. Of course, we can zoom into it and have a little look at it. Let's zoom in 100%. Where is node number 7? We just count 1, 2, 3, 4, 5, 6, 7. There it is. 96.1%. That's your best group. That's the best node in it. And the next best node is node number 10. It's 93%. Node number 9, 91%. And it's helping us, it's telling us how many, the gain here is telling us how many of the responders we're finding by doing this, or what the response, how many we're actually gaining. Well, I'm finding 31 here. I'm finding 31 responders here. How many responders were there originally? Let's just look at it. There's 135 people who responded in this sample. How many are we finding? Well, the first one finds 49, the second one finds 27, the third one finds 31, the fourth one finds 10 of them. You can imagine how this would be really useful if you had it cumulatively. If you were having it shown cumulatively, it turns out you can actually ask it to show in the output, you can ask it to show statistical cumulative classification tables and stuff like that. And you could say, I want show display cumulative statistics. Click OK, run it again. And now it's showing me the cumulative gains. It says, well, if you picked your top four groups, your top four groups would find 80%, 86% of the responders just in those top four groups. And this is why gains. Why is that useful? Well, because you got to think about it in terms of marketing or something like that, where you're saying, look, I know that I'm never going to find groups with more than 50% chance of responding to an offer, let's say. But if I pick my best groups, so if I pick my top 10 groups, how many of the responders would I find in my sample, and what would be the gain? What would be the average response rate to that? So that's kind of useful to know about to find these things out and to do that. So in that case, we might return to the decision tree. We might look at criteria again. What else can we do? Well, ask it. There is an aspect of estimation or of iteration, so you can do that. You can actually ask it to use a slightly stricter version of the chi-square statistic called likelihood ratio. I don't find it makes a big difference. And you can basically play around with it and give it a bit more freedom or be a bit more restrictive, make it a bit harder to create this tree until you come up with something which you feel is satisfactory and intuitive to you at that point in time. Did I have a question to Q&A? Could you also provide an example for the case where the target variable is not categorical but numerical? Well, yeah, you can do that. If you do that, I just swap it around. Let's just say, let's say I was trying to predict, let's pretend income was something like spend or something like that. If you do that, put that in. So this income spend. What's it doing now? Well, all it's doing is it's taking the averages. So instead of showing percentages, it's showing averages. I can show that if I put the charts in there, you can see they're just a little bit descriptive. So it's saying, oh, I shouldn't really use disposable income because that's a factor. That's an aspect of that's a function of income. Let's run it again. There we go. Okay, so here we go. Yeah. Yeah, so look, if I put that in there, it's saying, look, age is a predictor of estimated income. Um, and here it's if I zoom in on that, it's saying working in exactly the same way, saying that if you age under 24, then the average income is 13,000. If you're age 24 to 29, then it's 17,000. If you're age 29 to 51, it's 25,000, and so on. Now, the difference is, I don't think most people wouldn't regard decision trees based on where you've got a target variable, which is a continuous variable like this, as accurate as a categorical variable because they're averages. All it can show is averages. And as you can see, there's a lot of variation in each of these groups. But they're quite good exploratory tools. You know, it's a really good way to explore what factors drive that. So I think if you were trying to predict an outcome, like a continuous outcome, you would probably use some form of regression to do that, or a neural network or something like that, instead of a decision tree if you got a continuous outcome. But decision trees can play an important role if you if you're working with in exploring the data rather than necessarily predicting an outcome. Okay, let's return to our example here that we had earlier. Let's just chuck this out, chuck that back in, put home insurance back in up here. Okay, what else can we do? Well, in the output here, you can see that there's a lot of different stuff I can put in. I can ask it to show classification rules. So I can actually ask it to show me what rules it's creating, and I can have them in SPSS statistics or SQL. So that will actually generate rules for me, show me the rules. And look here, here's the code it's producing for it. Do I really need that? Well, you might want to. You might want to copy and paste it out there. You don't need it to do that. You can actually get it to automatically apply syntax to apply the predictions to other data. But it's just really to illustrate the fact that these decision trees can be rules. And you should also bear in mind that you have more than one decision tree type that you can run here. So if I go to, say, CART is a non-statistical method. That's called a classification and regression tree. It produces not necessarily a very different tree and not necessarily a very better tree, but if you were trying to play around with it, you find it only uses binary splits. That's one of the differences between a CART tree and a shade tree. It doesn't use chi-square values. It uses what's called a Gini coefficient. Looks for improvement. And you may find it's more accurate. You may find it's less accurate, but it's worth having a look at. And you should also bear in mind that you can build a tree based on more than one category. So you could have a tree based on one more category. I'll come to that in a second. Have I got an example of one of those? Yeah, I might do. I'll just have a look, see if I've got an example of that. I've got tree car here. But if you've got more than one category in your dependent variable, the tree does get harder to interpret because suddenly you're not just looking at, one group versus another group. You're trying to compare the values or percentages across multiple groups. Okay, let's assume that I built this model and I was pretty happy with it and said, look, I want to predict this. I want to use this as a predictive model. How could I do that? Well, one thing you can do is you can actually ask it to save predicted probabilities. So you could actually say, I want you to save scores for me, show me the predictions. This is using the CART method because I haven't changed that. Doesn't matter. But you can see what it's doing here is it's saying, look, this guy belongs to node 19, whatever node 19 is in the tree. You need to go and look it up. And I predict him to be in category two. Category two, I'm pretty sure is people who buy home insurance. To this category here. Yeah, category two. Why do I predict him to be in category two? Well, because I think he's got a 0% chance of being in category one and a 100% chance of being in category two. Why is that? Because presumably node 19, let's see if we can find node 19. Let's go back to the true. I reckon if we look at this, let me say, let's look in node 19. Zoom in a bit. Here we go. There's node 19. In node 19, everybody is in the yes group. So that's why it's predicting them, because he happens to be in node 19. Why is he in node 19? Well, because his estimated disposable income is greater than 13,000. He's got more than zero children. It says 0.05 here, but you could put in the ranges as text again. Make it easier. Higher than 0.5. children. It doesn't really understand integers. And estimated disposable income is split again here. So it's saying, yeah, it's actually it's between 13,000 and 14,886. And they have one child because it's 1.5 or less. So we know they've got one child. So it's kind of zeroing into that group. There's only 6 people in that group, and it's not very reliable. But that's why it's producing that prediction. Um, but if I went back to the data here and let's do the let's switch back to Chade. Click OK at that point. This is my decision tree with Chade, and of course it's saving probability values out here for me. Let's say that I wanted to just save away the model. So I just want to save away the model. I could go to decision tree here and I could go save. And rather than saving them as variables, why would you save them as variables anyway if you got the whole data set? Well, you could actually just add on rows of data onto the end. Some people just prefer to add on a whole bunch of row of data onto the end and just not have the target field in there, not have the values for the target field. So you just basically got some additional rows of data, but you don't know if they've bought home insurance, and it will still produce predictions for you. Or alternatively, you can export the model and say, I'm going to export this model. I've actually got it here already as insurance, but I'm going to overwrite it and hit continue and click OK. So I want to overwrite that and click OK. And then if I open up a new data set here, so I've got insurance scoring here, insurance scoring. You can see that it's also got 300 cases in it. But what doesn't it have? It doesn't have a variable indicating, I need to get rid of this because I've accidentally saved it. It doesn't have a variable indicating whether or not they bought the insurance product because they haven't bought the insurance product yet. And we want to use our model that we saved away as a little file to predict them. And to do that, we just go to utilities and we go to Scoring Wizard. Scoring Wizard is a place where you can select models that you've built using linear regression or logistic regression or discriminant analysis or neural networks or decision trees, and you can save them. You can pick up your XML file that you saved away. It's very simple. There's insurance and says, okay, I'm going to match these fields. Let's just say for whatever reason, one variable was called ink and the other variable was called income. You can't actually map it and say, oh, this variable income here is actually ink over here. So it's not even that fussy. It's quite useful and handy. It says, okay, I'm going to produce these predicted values for you, the probability being in the predicted value, and blah, blah, blah. I'll just ask for the predicted value and the probability being in that predicted value and the node number. Hit next and hit finish. And it just basically applies that and says, look, I predict this guy's going to be in node number group. He belongs in node number 7. I predict him to be a responder, and I'm 96% confident because 96% of the people in that group are responders. Now, in reality, if you only had like a really small response category, you like a 1% chance of responding or something like that, you're not going to find anybody with a 96% chance of being a responder. So what you might do instead is you might say, well, look, I want to look at everybody who's predicted to be a responder. You might select them or filter them out and say, oh, that's everybody, it's a 2, or everybody, or you might ignore that and just say, look, I just want to select, I just want to sort this in descending order. And I'll just select anybody who's got, a better than 3% chance or a better than 2% chance of responding. Anybody that belongs to that group is more than twice as likely to respond than my baseline. So don't think about that necessarily the predicted value. Think about the probability and whether the probability is better than your baseline. So that's something that's important to bear in mind. And we have one last thing I want to point out. Let's just see. I did have some other. Oh, yeah, here we go. Here's HR survey. I just want to show you. This here's an example to finish up on. This is like a little HR survey, and here we've got a key variable here, which is how long do you think you're going to stay with the company? And we've got 3 categories. Look, 1, leave within 2 years, 2, leave 2 to 5 years, and 3, remain at least 5 years. That's going to be my target this time. If I go to classify down to 3, I'm going to make that my dependent variable, send that across. I think I can just pick up everything else and just chuck it in. Let's just see. You get the idea. Oh, I'm going to change criteria just to be on the safe side to 40 and 20. Okay, then click continue with that and click OK. And you can see the tree's quite shallow. Otherwise, zoom in on it. 100, 100. You can see it's harder to interpret, can you see? Because there's three values. So I find in those situations that I really like to use the charts because gold indicates these are the guys that remain at least 5 years, and blue indicates these are the people who say they'll leave within 2 years. And it's really interesting what drives that. You know, if I just change this to say 120% to zoom out a bit, it's attitude of senior staff. If they say less than or equal to fair, then most people are going to leave. If they say better than good, most people are going to stay 5 years. And if they say the working hours are, you know, better than good, then you're up to 96% of people. So if you wanted to figure out for this company what are the things you needed to get right to retain staff, it would be attitude of senior staff and working hours and what are the things you don't want to get right. Well, if they didn't like the working hours and they didn't like the attitude of the senior staff, then 95% of them are going to leave in 2 years. So again, very powerful, very easy way for us to explore the data and to see relationships. So yeah, there we have things like drivers of satisfaction, other applications. Sometimes you might be doing a demographic profiling. Here we have people who are in a minority category versus people in a non-minority category. And one could figure out, you know, where these groups tend to cluster within the data by looking at things like employment category and age and months since hire. Or even things where you've done cluster analysis and you've got four cluster groups and you're trying to figure out, well, what makes cluster group four different from cluster group one? Well, cluster group four are people who buy beer and who buy canned vegetables, so you can see that. And cluster group one tend to be people who do not buy beer, do not buy wine, and do not buy confectionery. You know, they're buying something else. Whereas people who cluster group three here are people who don't buy beer but do buy wine and do buy canned vegetables. Yeah, so these are the cluster group nine. There's a lot of them in there, so it's a really good way to kind of help us interpret. Just you should be aware that online training materials that we have are available free to our customers, or they're available for purchase. And we've got one on we've got a training course that I've written called Working with Decision Trees using these sorts of examples. Goes into a lot more detail, the ins and outs of decision trees. And you should be aware that working with Smart Vision Europe, we can help with the processing and analyzing of your data generally. And that could include self-paced virtual in-person training, how to use SPSS products and appropriate statistical techniques, or a mix of consultancy and training whereby we do the initial work and then teach you how to replicate it. You can also source your SPSS software directly from us. If you're already an IBM customer, you can transfer your license to us and we'll look after it. You'll have access to our training materials, of course. We also provide, as I say, training, formal training, and custom course development, and formal bite-sized training. We offer no strings attached technical and business advice to all things related to analytics to all comers. And we offer track technical support services around the IBM SPSS product line with support tickets and everything. I do hope you found that useful. At 3 o'clock, I think we're going to do another webinar. This time we're going to be looking at linear regression and an introduction to regression techniques in SPSS. In the meantime, assuming you find that useful, we look forward to you logging in again in the future. Thanks very much.